Hello student, welcome to our physics discussion, that is physics in a smart way. In the last video, our discussion was, the topic was thermodynamic work, and as you have discussed, you have found out that the formulas that we have gone for are very simple, that thermodynamic work or work in a thermodynamic way can be expressed either in the form P into delta V. There, we don't have to be so careful on vector direction and all those things because mostly the work is done in a cylinder piston arrangement. So P into delta V, that is your pressure into final volume minus initial volume. If final volume is P1, initial volume is V0. So that is like this. But this formula is valid if the pressure is constant. Throughout the process, pressure is constant. If the pressure is variable, then we know what equal to our integration of PdV. We have to go for very small amount of work. The pressure at a particular point, small change in volume, we have to go for a small amount of work and all those things. That is integration of PdV. That is for a case where pressure. In fact, it's a universal formula. Pressure may be constant or not constant, doesn't matter. But essentially, if the pressure is constant, why unnecessarily we go for integral formula? That won't help us. But if the pressure is not constant, then we got the way to find out the work is like this. There is a third way, as I have introduced, that is with the help of graphs, with the help of thermodynamic graphs. There are some words like state. Your state means state of a gas, state of a gas. We talk of the state of a gas. When somebody considers a living being, animal or human being, and talks of the state, then state has got a different connotation. But considering the state of a gas, the state that we are considering is scientific state of a gas, and because gas cannot talk just like you, whether it is in a happy mood or remorseful or whatever it is. So thereby, I'm here particularly very interested to find the scientific state. The scientific state of a gas is usually expressed by scientific parameters like pressure of a gas, volume of a gas, sample, its temperature, and quantity of the gas, that is number of mole, N, and the type of the gas. What type the gas is, monatomic, diatomic, like. So usually with these quantities, we express the state of a gas because once we know for a gas how much is the pressure, how much is the volume, how much is the temperature, and all that. So thereby, we can be able to predict what the gas is going to do. And to express it in a symbolic or graphical form, we take the help of graphs and all that. Just a minute. Just a minute. We take the help of graph because graphs they they help us in creating pictures, and pictures always suit a human mind. Human mind is more compatible with pictures. But so far as pictures is there and so far as graph is there, graph has got only two variables. If you have to use a graph and the graph is to use three variables, then you have to go for a computer simulation and three-dimensional graph and all those things. That we cannot do on a two-dimensional scale. But there are so many variables here, so many parameters here: pressure, volume, temperature, type of the gas, and number of moles, and all those things. Basically, once the gas is fixed, we got number of moles fixed and type of the gas is fixed. Okay. So once we are ascertain on those things, so basically the things which continuously change are pressure, volume, and temperature. So there are three variables, but so far as graph is concerned, we got only scope to use two variables. So thereby many different type of graphs can be done. That is selection of two objects out of three objects. Selection of two variables out of three. The total that is three. My point is we may take pressure volume leaving out temperature. We may take pressure temperature leaving out volume. We may take volume temperature and leave out pressure and all those things. So many different graphs can be drawn, and usually we see all those different graphs. The most important graphs so far as will be using each pressure volume graph. On y-axis usually you got pressure and x-axis you got volume. There, if you put a dot, on that graph, we know a dot or a point on the pressure volume graph or on the graph means a point must be having its x-axis and its y-axis. Y-axis is pressure, x-axis is volume. So thereby, once you got for a particular gas, once you got a point, so point has got x and y coordinates. So thereby, we got to know how much is pressure, we got to know how much is volume. If we are not given that, then we cannot ascertain the point. And using the so-called, you must be knowing it, so-called universal or the most general formula, that is PV equal to nRT, universal gasification, PV equal to nRT. We know once pressure and volume they are given, number of moles you must be knowing, and R is universal gas constant. We will be getting to know how much is temperature. So thereby we know pressure, we know volume, we know temperature. Okay, but at least here, if you got a point fixed on the graph, then you know that is pressure and volume. At least on these issues they are in. If you do not go an extra length in finding temperature and all that. But once the gas changes the state, then you know state when the gas changes the state means the parameters will be changing. Maybe the pressure is changing, maybe the volume is changing, maybe the temperature is changing. Usually once you select a gas, number of mole and type of the gas is constant. They can also vary, but we do not take all those complexity. But at least pressure, volume, temperature, any two of them can change. All the three of them can change. Okay. So thereby we know the point won't be fixed in coordinate space. If the pressure and volume they are changing, then the point will start to shift. When the point starts to shift, we say that a process is getting done. So basically, a thermodynamic process means the change of the state of a gas, pressure, volume, temperature. They are changing any two, any three, any two, any one, or all of the three and all that. So thereby, if we say the gas is changing from a state one to state two, then the curve, the graph that you have shown from 1 to 2, which can be a straight line, which can be a curve, doesn't matter. That depends on which way the things are changing, which way the states of the gas, the parameters are changing. So thereby it can be a straight line, it can be a curve. But 1 to 2 is a process. We can say that is process, that is 1 to 2. When the state of a gas changes, then process is made. And within that process, we can think of the work anyway. So because I have to have some free space, let me remove something. Okay, let me have some clear space. In the graph that is shown, we know That is a pressure volume graph, typical pressure volume graph. And in the pressure volume graph, as I told you, there are so many types of graph can be done: pressure volume, pressure temperature, or volume temperature, involving other parameters like entropy, and all those things, enthalpy, entropy, all those things. So many different graphs. Practically hundreds of graphs can be done. But one of the graph is very, very important. That is pressure volume graph. In the graph, as I have shown, the gas initially was in a state 1. The pressure is V1, volume must be, that is V1, volume must be V1. Sorry, here is the volume, okay? And the gas, it changes the state from 1 to state 2, that is pressure is V2, volume is V2. So thereby the volume must be V2, that is like this. So in the process, as the gas goes through, if you try to find out how much is the work, because pressure is there, which is non-zero, which seems to be non-zero, and there is certain volume change. So as per our previous idea of work, you know that must be some work. If you try to find the work, then because you have seen as the gas goes from process 1 to 2, many different type of pressures are achieved by the gas, and gas goes through all, or one may say gas goes through many different pressures. So thereby we know our work done. We know our work done must be by the second formula, that is integration, that is 1 to 2 integration PDV. But do you know integration PDV? Already you have done that in our basic integration. In the 11th question, you can go to my 11 calculus. The integration PDV, as the diagram shows, that is PDV is a very small area. So integration PDV is nothing but the area under the pressure volume graph, that is going from 1 to 2. So thereby, as it is discussed already, I won't elaborate on it. That is area under the graph. That is area under the graph. Area under the graph. Okay. If somebody wants to find out here in the previous diagram, in the previous graph, if somebody wants to find out how much is the work done as the gas goes from 1 to 2, so thereby we know the work must be equal to the area under the graph, or area under the graph, starting from the graph onto the volume axis, the area under the graph, that is equal to 1. Okay, so work done can be found out. Work thermodynamic work can be found out by either P delta V formula or integration of PdV formula, or directly if the graph is given and some visibility is there, then that is area under the graph, the suitable area under the graph. So these three things. So thank you for your cooperation, for your kind ear. We shall be going to the next issue in this. That is maybe the first law and all that. And those things can be quite interesting.